Okay, so the last video we did basic counting, dominoes, and outfits, and restaurant dinner combos, where we were just multiplying things. I want to do two more of those right now. Basically, it's the fundamental counting principle, right? When we're just multiplying. Let's talk about passwords. We're going to keep this super simple. Not real life that we all know about passwords. We're not going to worry about special characters or the difference between lowercase and uppercase. None of that. Let's say most basic password has to have 8 characters and it must start with a letter. 1, 2, 3, 4, 5, 6, 7, 8. Has to be a letter. Now there is no other restrictions. So 26 letters in the alphabet, 10 digits. So these are 36. So 26 times 36 to the 7th power. And see, my TI-83 should definitely be able to do that. Oh, Lord. Three, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so that's million, billion, trillion, over 2 trillion. I did not write all the separate decimals. I was just trying to deal with the scientific notation of the 12. So if you'll put that in your calculator, make sure you're getting over 2 trillion. Let's work on phone numbers now. Now this was one that I spent probably 45 minutes one day trying to research different restrictions. Obviously, I could not find all the restrictions, so this is still the simplified version. But you know, you have an area code. The next 3 numbers are actually called something. I don't remember what they're called. Then you have the last 4, okay? I did read that what we mostly call our phone number, right? The first one, you cannot have a 0, you cannot have a 1. I found quite a few restrictions for the area code. Again, I am sure there are a lot more, but let's just go with what I was able to find on the internet that day. Okay, I had read that area codes have to be between the numbers 201 and 999. And then I also started listing area codes that are not allowed for just normal people, right? These are the toll-free numbers. 555 is usually reserved for like the numbers that they'll say in movies or songs or something. So, and I'm sure there's a lot more. We're just going to go with this. Now, this is the easy part, right? You could have 8 numbers there. And these are, of course, 10 for the digits 0 through 9. Now, and okay, if we could figure out this part, then we'll just subtract 5 from it, right? So here's a question that many students get wrong, and this has nothing to do with counting or Math 207. It's kind of a useful skill to have. How many numbers between 201 and 999? And that does mean inclusive. We were allowed to use 201. We were allowed to use 999. Pause me. Take a second. Figure that out for yourself. Okay. Most students come back and say 798. And that is not correct. It's 799. Because think about it. If you're not convinced, how many numbers are between 9 and 10? Remember I said you could use that number and you could use that number. You can use that number and you can use that number. Well, there's 2 numbers, right? the number 9 and the number 10. But when you do the subtraction, you're only going to get 1. So you always have to add 1 to it. So it's not 798, it's 799. But now we have to subtract off those 5 we're not allowed to use. So that's 794. So now we have basically 794 times 8, So it was going to be way too hard to go digit by digit here. So what I really did was just view this as a 3-digit number, meaning instead of seeing the digit 2, the digit 0, the digit 1, I viewed this as 201, 999. That's a nice little trick here. 794 times 8 times, so we got 794 times 8 times 10 to the 6th, which is over 6 billion. Okay. All right. Now we're going to switch gears a little bit. That was just to pretty much finish up the last video. So first, to get the most out of this, if you would not look at the notes right now, you may have already done so, but if you haven't, don't look. Pause the video and try to do this. So let's say we have 4 errands to do. You could call the errands A, B, C, D, just to keep it easy, right? How many ways to do them in order? Meaning, am I going to go to Target, Walmart, CVS, Martin's, or am I going to go to Martin's, Target, CVS, Walmart? The order matters. Okay, see if you can get set up in a tree diagram and get a feel for how you could organize this. Then you can come back to the video. All right, so here's one way. Let's say I started with A. Well, then I could go to B, C, or D next. Okay, now if I did A, B, I could go to C or D. If I did A, B, C, well, then I'd have to go to D. If I did A, B, D, I'd have to go to C. Now, if I did A, C, I could do B next or D next. And if I did A, C, B, I'd have to go to D. A, C, D, I'd have to go to B. If I did A, D, I could do B or C next. If I did A, D, B, I could go to C. A, D, C, I'd have to go to B. So there are 6 ways right there, right? And that started with going to do errand A first. Well, you can imagine you do the same thing with B, same thing with C, same thing with D. So each of those would have 6. 6 times 4 is 24. We're not doing tree diagrams anymore, right? But I wanted to just take one more chance to show you, depending on what grade you're teaching, this is a way to get them to see the 24, so they don't have to just believe you that it's 24. But let's do it a slightly easier way. All right, put your dashes. The first chore I'm about to go do, well, there are 4 that I could pick from, right? Martin's, Target, Walmart, or CVS, okay? Next, so this is the first chore, that's the second chore, that's the third chore, that's the 4th chore. When I'm on my second chore, well, I've already done 1 of them. So this is kind of like that without replacement, right? There's only 3 more stores I could pick to do next because I'm not going to go to the same store twice. By the time I get to my 3rd chore, I only have 2 more stores I could choose to do times 1. This is 4 factorial. In case you haven't seen the factorial sign lately, the definition of factorial is multiplication all the way down. All calculators have that. If you're on a TI-83, because about half of you are, I don't think I can ever get this to show. Well, I'll just talk slow right now. If you have a TI-83 in your hand, you can put the 4 in, then go to Math, move over to PRB, which stands for probability, and see that fourth choice, it's the exclamation point. If you have the smaller calculators, it might actually just be like a second function of one of the buttons, or a lot of the smaller calculators, you have to locate the PRB function and you'll find it in there. I'm sure a quick Google will tell you where to find it. We're not going to have massive numbers anyway, so it doesn't take that long to go 4 times 3 times 2 times 1. All right. This right here actually has a name. Remember we said order was important. So this was more of a example before we give you the rule. It doesn't really have a name for the rule, but if you have n things and you have to order them all, order, arrangements of n elements is n factorial. Maybe I should give you some synonyms right now because it's going to come up a lot. I think I put them on the next page, but well, maybe not. Oh, yeah, okay. These are all buzzwords, all clues for you to know that order matters. They'll talk about order or arranging or lining things up or putting them in a row. That idea that I'd be able to tell which one was first or which one was on the left, that type of thing. The most classic examples are putting up picture frames on a wall. Now, if you're not really into decoration, this is not going to make sense to you because you probably just stick them on the wall wherever. But if you are into decorating, you probably understand that depending on what picture you put on the left and then which one you put on the right, it's going to give a different feel for what that wall looks like, right? Now we're starting to move to a subset. Let's say I have 5 frames and I'm decorating my room, but I only have room to put up 2 of them on the wall. There's not room to put up all 5. What if we have 5 frames and only put up 2 in a row? How many ways to do that? So again, we are putting them up in a row, so it matters who's on the left, who's on the right. Well, for the spot on the left, I could pick one of those 5 to put there, right? But then when I get to the next spot, the one on the right, I've already used up one of my pictures. I only have 4 more sitting on the floor that I could choose from. So that is 20. Not hard. Now, I'll be the first one to tell you, sometimes we then give you mathematical rules that seems to complicate things. But I'll tell you why we end up making rules. Probably not for a problem like this. This one is pretty basic, doesn't take very long to figure out 5 times 4. But let's put up the rule and then we'll talk about it. I'm going to try to put it up, just like your book does. Okay, these things are called permutations. You have to know that permutation means order matters. So the number of permutations of a subset, meaning I didn't put up all my pictures on the wall just a minute ago, right? I only put up a subset of them, of a subset where I have n items total, but I'm only arranging r of them. That would have been like my 5 frames I had, but I only wanted to put up 2 that were on the wall. I want to show you different notation. The notation in the last 10 to 15 years looks like this. A P parenthesis N comma R parenthesis. A little more old school, like when I was growing up, we wrote it NPR. So you'll see both of those depending on what calculator you're on. Here is just trying to show you, just a minute ago we said 5 times 4. 5 times 4, because we were putting up 2 of the frames. So this is really just telling you, listen, you're going to multiply them all, right? Here is the shortcut though. It's n factorial divided by n minus r factorial. That looks real confusing, right? Let's back to our picture frame, the problem we just did. 5 frames, put up 2. Okay, so that says that would be 5 factorial over 5 minus 2 factorial, which is 5 factorial over 3 factorial. When I was growing up, we had to do this stuff by hand. It's really cool what happens though. 5, 4, 3, 2, 1 for the 5 factorial. 3, 2, 1 for the 3 factorial. Look, all that cancels. There's our 20. So these short problems, doing a permutation is a bit overkill. I'm pretty sure I could have multiplied 5 times 4 in my head. But sometimes the problems are a little bit longer. So again, on the TI-83, you can actually put the 5 in, go to Math, like we did a minute ago, PRB, and you're going to see the NPR button. When you hit NPR, then you have to put the 2. I don't know. Hold on. Oh, maybe if I light it up, it's just that things are backlit. So see, I got the 5 NPR2. I hit enter, and I get 20, of course. Again, overkill. But imagine, we're not going to do this because I don't think our calculators could handle the numbers. But let's say I'm a real fancy museum in New York City, and I have 1,000 pictures that I can put in a big gallery. And I know that I want to put up 200 of them. Well, I don't know that I feel like going 1,000 times 999 times 998, 200 times, right? If you have 1,000 frames and you're putting up 200 in a row, you do not want to have to multiply 200 numbers on your calculator. The NPR button is going to come in very handy. I just totally made this up. I don't even know if my calculator will handle it. So hold on a minute. Oops, I picked the wrong thing. Yeah, my TI-83 doesn't even have enough memory. Of course, computers would. But that's why these formulas, of course, are programmed into calculators and computers. Most of the time, though, it's overkill for us. Just putting our dashes and figuring out 5 times 4 is a much more efficient way. All right, let's do a couple of classic problems. They're usually arranging people to take pictures or books on a shelf or different things like that. Let's say we have 8 athletes to be photographed. For some reason, we care where they stand in the picture, so you cannot overthink these things. I can't tell you how many times I saw my own daughter's sports teams get photographed, and I'm pretty sure they didn't care where the people stood. But that's not what this problem is saying. It says how to line up 3 of them. So we can put our 3 dashes. Well, there's 8 people I could choose to be on the left. Well, once I put a person there, I only have 7 people to decide who's going to go in the middle. Then once I put a person there, I only have 6 people left to decide who's going to go on the right. This is 336. Very easy. But again, just to highlight that this truly is called a permutation. This would be out of the 8, you have to line up 3. And just to remind you what the formula would be, 8 factorial over 5 factorial. Remember, that's the 8 minus 3, which is 5, if you're using your calculator, but I still think it's just as easy to multiply those 3, right? 336 ways. Okay, let's do a slight harder one. I must have found this in your book. We're going to arrange, so this is all about books. We're arranging 4 algebra, 3 chemistry, and 5 history books on a shelf. How many ways to arrange? So that's really indicating to you that order matters if they are grouped according to subject. Okay, so, well, they're staying in their piles, like the algebra ones have to be together, right? So let's think about the algebra. There were 4 of them, and we're arranging all of them. So this would be 4 factorial. This kind of goes back to that original how to arrange n items from n things as n factorial, that first rule I gave you. Chemistry, 3 chemistry. And remember, for each way to arrange the algebra, you could then put all the different arrangements of chemistry. So this is multiplication. If you can imagine, you wouldn't want to, doing that tree diagram, any one of those is going to have all the chemistry choices. Then the next one is going to have all the chemistry choices. So we definitely have multiplication in there. Same thing with the history. 5 factorial. Now I'm going to be honest. The first time I did this problem, I did it wrong. I was probably rushing, grouped according to subject. So I did that. I'm like, I'm good. And then I'm like, what? Well, particularly because my answer didn't match the back of the book, right? I'm like, what am I forgetting? I'm like, oh, look at what I've done here. By the very nature, I made algebra come first, then chemistry, then history. We can arrange the subjects. You know, maybe I'm going to put my history books first, then chemistry, then algebra. So you need another 3 factorial there. So this is 24 times 6 times 120 times 6. There's 103,680 ways according to the criteria they gave me in this problem. I'm going to add an extra piece to this problem that the book didn't. I mean, sure, that's a fascinating number. Okay, I don't know who's doing this to the bookshelf. This doesn't hit me as hard as the next piece I want to do. So we still have my 12 books here. Oh, I'm sorry. Before I do that, though, I apologize. You know, on the algebra, how I said 4 factorial? Usually someone will raise their hand if we're in the classroom. They're like, well, isn't that a permutation? You know, you went back to that first rule you gave us. I mean, but what about this permutation rule? You can do this as a permutation. This would be 4 permutation 4. I've got 4. I need to line up all 4. So if you were doing your formula, it would be 4 factorial over 4 minus 4 factorial, 4 factorial over 0 factorial. You may not know this, but 0 factorial by definition is 1. So yes, this is 4 factorial. That's why they gave you that first rule. Even though the permutation rule absolutely takes care of it, instead of having to do all that, it's much simpler to know that if you're arranging all of them, it's just the 4 factorial. All right, but back to the second part that I want to ask on this. Let's just, I know I didn't call the first part A, but I'm going to call this part B. So maybe I'm not OCD and psycho. I don't care about keeping them according to subject. I've got 12 books, and because most of us probably have 12 books in our home or at our dorm or apartment or something, right? 12 books is not that much. I mean, usually if we're in the classroom, I'll actually have 12 books on the table to show you. It's just not that much. Picture what that looks like in your head, okay? I just want to know how many ways to arrange the 12 books on a bookshelf. I don't care about subject or anything. Well, there's your 12 factorial, right? Guess what that number is? This always fascinates me. I still have fun in math. 479 million ways. I'm sorry, I cannot wrap my mind around that. I can picture 12 books. And I'm arranging them on a bookshelf, probably only 2 or 3 feet long, right? There is close to 500 million ways. I still sometimes think that is so beyond fascinating that I'm actually sitting here checking my math right now. Yes, that is correct. That blows my mind. So again, if you can get your kids to experience it, not that they can wrap their minds around 500 million any better than I can, but it is fun to see how big numbers can get. 12 books is not that much. All right. Moving ahead a little bit. Here's another classic problem. Let's say we have 5 students, but we need to pick a president, vice president, and secretary, okay? So this is that idea of certain jobs that, even though they don't use the word order or line up, it's important that I know who is president, who is vice president, and who is secretary, right? So you can almost view that as a lining up when they're telling you they have certain jobs. Okay, and how many ways to pick those 3? Okay, you could picture. There are 5 people to pick for president. Well, vice president, you can't have both jobs, right? So we're down to 4. And then secretary, we're down to 3. There are, bad math, sorry, 60 ways. Because it's very important that I know, because each one of those, they have different duties, right? Now, we need to compare that. Let me write my 60 up here so I can fit all this on one board. I'm just going to write this a little bit smaller. President, vice president, secretary. I'll put a little line here, but I want to keep that up. Big old butt. Okay, so what if we just need 3 of the 5 people to come help move chairs? Like maybe there's an assembly going on. I don't know. The school I went to, they were always making us move chairs from one classroom to another, right? Nobody has a special job. It's just like, please grab a chair and move it down the hall. There is no particular job. You're going to kind of see a new word coming now. So basically, how many ways can I grab 3 kids from the 5 and say, come with me, we're moving chairs? Again, it doesn't matter who I grabbed first, second, or third because nobody has a particular job. I really, really, really want you to try this right now before you look at the next page of notes. I was actually going to stop the video here and then start a new video so you wouldn't look at the answer, but don't look at the next page of notes yet. Take 10 minutes to see if you can get organized and come up with how many ways. Again, you can call the kids A, B, C, D, E if you want. I promise you, it is not 60, okay? It's a whole lot less, so this is not a massive amount of work, but it's just really trying to figure out how can I get organized that I am convinced that I've listed every possible way. And that's what organization is. If you just start randomly putting some things on your paper, you're not going to know if you listed them all, right? So you have to have some type of methodical way of staying organized. So pause me, try that for 10 minutes, then come back. Okay, 5 kids, we need to grab 3. Okay, here is one way. There are other ways to stay organized, but I just want to show you one way. I don't have really a word for it. I kind of call it the moving forward. Let's say I grabbed person A and grabbed person B as 2 of my 3 people, right? Well, then I could grab C, D, or E to fill out my group of 3. Okay. Well, let me keep with person A. Now, I've done every possible way of having person B in there, so I'm skipping person B now. And I'm going to go to person C. Then I could fill it out with D or E. See what I mean by going forward? Okay, those are all the choices for B. I've listed all the choices for C. So I guess I'm going to skip B and C now. I'm going to go straight to D. Well, I'm almost out of people, so A, D, E would be the only choice I have left. So what I have listed so far is every possible group that's going to have person A in them. So I'm done with A. Now let me start with person B. Okay, I could do B, C. I could still fill out the trio with D or E. All right, now I've done everything with B, C, so now I'm going to do B, D. Oh, I'm already out. B, D, E is it, right? Because I'm out of people. All right, so I've done all of A. I've done all of B. Now I get to start with C, and again, I'm always moving forward. I'm not going to do CB because I already took care of that in there. So you're not going backwards. You got to keep moving forwards. C, D, E. Okay, well, I'm out of people. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 ways. As long as you came up with 10 and it was methodical and not lucky, you're good to go. It does not have to look like this, but this is a popular way to stay organized. So hold on a minute. When I was giving them certain jobs, it was 60. Now it's 10. There must be some type of pattern or relationship between the two. Let's see if we can talk that out before we get formal. So again, we had 5 kids. We picked 3. When they had jobs, we had 60. When we were just grabbing them to move chairs, we had 10. Now, if you just look at the numbers, it's like, oh, you divided by 6. But I don't know, is it always a divide by 6? Well, let's just look at, and I'm going to purposely kind of write those 3 people almost in a bubble, okay? Because I don't want you to get confused and think there's any order. Let's say person A, B, and C help me go move chairs. Think about that little trio, though. When they had a job, I would have needed to know Was it ABC? Was it ACB? BAC? BCA? CBA? CAB, right? Because it's that president, vice president, secretary. This one trio has turned into 6 things when you have jobs. So we're kind of starting to see where that 6 comes from, because there were 3 things in there. 3 factorial is 6. All right, I really feel like there is a pattern developing now. And now I'm going to give you the formal rule for it. And once I put the formal rule up, you may want to come back and look at this. It might help it make more sense. But this little trio, if they don't have jobs, well, it's just one trio, right? But if I have to assign them different jobs, that's that permutation, or arranging n things from n things. That 6 different ways that that trio could be given jobs. So when we do not care about order, or we're just grabbing people, it's called a combination. Now, what I was trying to show you in the last problem we just did, it seems like it's the permutation divided by r factorial. That was our 60 divided by 6 divided by 3 factorial. Here is the formal notation. Combination, again, C and R or NCR. Those are the 2 most popular ways. I do want to make sure I show you a very old school way, because I never know if you're going to the internet and going to find a very fancy website. The notation I grew up with is N choose R. This is how we say it. N choose R. I want to make sure you know I did not forget to write a fraction sign. This is not a fraction. This N just kind of floats over top of the R, and you put big parentheses around it. If you ever see that notation, it means combination. Okay, and the way you say that out loud is N choose R. Choose is another synonym for grab. So we said it's permutation, which that was our formula for permutation, right? Divided by r factorial. Here we get to review fractions a little bit. Hopefully you know, anytime you have a 3-tiered fraction, you can put the 2 denominators together. Check that out with some easy numbers if you're not convinced. That is the formal formula for combination. But again, most of the time we're not going to have to work that out. Calculators and computers have been programmed with that. But that's why combinations are always smaller numbers than permutations. We had 10 instead of 60, right? Because you're dividing by another value. Yeah, so if you're looking at the notes now, here's all those synonyms I was trying to give you earlier, so I won't write that up. Combinations, very real life. Whether you play the lottery or not, we often hear if the lottery has gotten to some, massive amount, 900 million, and everybody's flocking to 7-Eleven or whatever. And all lottery, whether it's online or if you're in 7-Eleven, you can pick up the little pamphlet. It will tell you the, I was going to say the odds. I hope they just say the probability of winning. So the big lottery, not those little pick threes that I think they do every day in Virginia, but I mean the one that is like twice a week and it crosses state lines. They actually, I think, changed it a year or a year and a half ago. So the numbers I'm about to give you, don't quote me on this because they may have been changed in the last year. But let's do this lottery that I'm talking about. You have to pick 5 numbers between 1 and 75. Now the big, and then you have to pick one, what they call a mega ball, and he is somewhere between 1 and 15. And the big lottery, order does not matter. The only reason you ever see everything in order, like in the newspaper or if you're looking it up, that's just to help people be able to check their own lottery ticket. Like if the numbers 7, 41, 2, and 5 came up, when the little ping pong balls are blowing up, I know it's not enough numbers. That's not the way they're going to list it. They're going to list it 2, 5, 7, 41, just to make everybody's life easier. So order does not matter. Thus, this is absolutely a combination. All right, so this first thing, I just got to pick 5 between 75. So that's 75, choose 5, combination. But this extra little mega ball gets tacked on to every possible lottery number right there. So times basically 15. For every possible lottery number, for every possible group of 5 numbers, each one of those could have the numbers 1 through 15 attached. If you put that into your calculator, you will come up with this. And yes, about 260 million. And that is usually, if you ever hear about what the odds of winning the lottery is, most people just say, yeah, it's like 1 in 250 or 300 million. That's where that's coming from, combinations. That's why it's probably not worth you spending your $2 to buy a ticket. Although, of course, someone can argue with me. If you don't ever buy a ticket, your probability of winning is 0, right? If you do buy a ticket, well, it's just a hair above 0, but at least it's not 0. All right, let's do a few common problems. Yeah, so now I'm kind of looking at, because I do not want this video to be too long. We're going to do 2 more problems. I'll give you homework. Then there will be another video just doing a little bit more of this topic with some other things. Okay, so this one's not the easiest because it's putting specific criteria. First of all, these are study groups. Don't overthink this. This is not maybe a lab project where someone's doing Excel, someone's doing the research, someone's, typing it up or whatever. These are just study groups. You're meeting in the library and, you just got to sit down and start talking or something. So no particular job, definitely a combination. All right, how many study groups of 2 males and 3 females can be made? So see, I'm not just grabbing 5 people out of 30. I have to split it up. So out of my 18 males, I need to grab 2 of them. So that would get me a bunch of duos, a bunch of pairs of men, right? And for each one of those pairs of men, I would have different trios of girls. So out of the 12 females, I have to pick 3. Now, if you're careful, the numbers on the outside, the first numbers, that should equal your 30 people total. And then we needed to have study groups of basically 5 people, the 2 plus 3. So that should give you 33,660. All right. Right now, I'm going to keep going with this problem because I know the book does quite a few of these. So sometimes I swear this should be part A, and we should reverse these, but again, I'm mirroring something the book does, so that way it can help you with your homework. Part B didn't give us any special, specific criteria. They're just like, hey, pick 5 people out of the 30 to be in a study group. Okay, I had 30 humans, and I need to pick 5 of them. So this was much easier than part A, right? Okay. I need to write part C very carefully because I know a lot of students get confused on the wording. So first, when they told me, I'm just going to write my numbers down here so I can erase. And then just group of 5 was 142, 506. Okay. What is the probability that when forming a study group of 5 people, we end up with 2 males and 3 females? So what is the difference? The biggest difference between A and B is A and B, it said how many ways. That is counting. Numbers bigger than 1. This says what's the probability. So this has to be a number less than 1. Think about a fraction. So in general, you're going to put like sort of the no restriction, just how many ways total. But then the specific restriction is the numerator, right? So the whole 2 male, 3 female, that's our numerator. Because not every group of 5 had 2 males and 3 females, right? But that's the specific thing they're asking me about. Out of just generically, how do we pick 5 people out of 30, which was our 142, 506 from earlier. So this turns out to be 0.2362 or 23.62%. The book has a few problems that talk you through basically the numerator and denominator separately, and then they have you put it all together in like a part C. Let's do one more, kind of bringing this all together. It's going to be part D. Same problem, or same setup of the problem. So we still have those 30 people, 8 males, 12 females. We're still picking a group of 5. Okay, I kept that the same. But I want to know what's the probability I end up with a study group of all females. So all females is the very specific. That's going to be the numerator. Just total in general of picking 5 people from 30. We already know that number, right? But maybe let me just write that out again. The 30 choose 5, which is that 142, 506. Okay. But now I need all female. I mean, if you want to think about it, from the 18 males, you were choosing none of them. And then from the 12 females, you were choosing 5 of them. So I'm just trying to, you don't have to have this term right here, but if you wanted to look, yes, the 30 matches the 30. The 5 matches the 5. So you can make sure that you took care of everything. See how 12 plus 18 is 30, 0 plus 5 is 5. Again, you don't have to write that part, but I think it really helps highlight that I did think about all 30 people. I just didn't happen to want any of the men this time. So the numerator is just 12 choose 5. If you do 18 choose 0, it's by definition 1. And this probably makes sense that it's a pretty small chance that I would end up with all girls. I mean, especially given that there were 18 guys I could have been choosing from, right? So hopefully that makes sense that it's a whole lot smaller than our answer from part C. All right, given that I want to stop the video here. I just got to tweak my homework a little bit. So let me take a second to look at what I was going to assign and think about what I really want to assign. Okay, so again, there's only one tiny other thing that I haven't gotten to. The book covers it, but worksheet 1, those problems absolutely are based off of what I just did on the video. I'd say 95% of the problems that I have listed on chapter 33.2 are based off of this video. There might be 1 or 2 questions you get slightly stuck on. If you find that happening, just watch the next video because we will be covering it. But most of that stuff is based off of this video. So I'm going to leave it at that. All right. We'll see you next time.